Hello friends, my name is Shifa Mohammad Ayaz and I'm a third year electronics student, and today I'm going to teach you my fourth experiment, that is design of a practical differentiator using opamp OP07. So let's get started. So here is my Word document which I had prepared. Okay, so here we are gonna implement a practical differentiator. The only difference between the integrator and the differentiator is that at the initial stage, we are gonna attach a capacitor at the input terminal where we are feeding the input signal. So that is the basic difference between an integrator and a differentiator. And the differentiator's output in terms of frequency response is essentially a high pass filter, so which is totally an opposite of the integrator circuit. This is how your circuit looks like. So first we would begin with the calculations where FA and FB are given to us. FA is equal to 1 kilohertz and FB is 10 times of FA. So here I'm considering it to be as 10 kilohertz, and I'm making an assumption where my C1 is equal to 0.1 microfarad and CF to be equal to 0.01 microfarad, and the formula for FA is equal to 1 upon 2 pi RF into C1 and FB is equal to 1 upon 2 pi R1 C1. Using these two formulas, I have derived the RF and R1 values, which is where RF is equal to 15.91 kilo ohms and R1 is equal to 1.59 kilo ohms. And here is how your practical differentiator created in LTSPICE looks like. Okay, so and this is the observation table which I had recorded, and it is similar to the integrator circuit part which I had shown in prior. Similarly, I've recorded those observations in the same manner, and here I'm going to show you the output waveforms when I'm feeding sine wave as an input signal, square wave as an input signal, and rectangular wave as an input signal, and uh, checking out the different output waveforms achieved from these input signals. And finally, we would be seeing the frequency response and the phase response. So, okay, let's get started with it. Now, once you launch your LTSPICE, build this circuit where I have supplied sine wave as an input signal and I have set all my parameters to the circuit. Just save this circuit and run it. And here is the plot pin available. Click your probe on the V in part. So this is your regular sine wave and the V out part, that is your output waveform. So let me change the color if this so that it is very much visible to us. Okay, so this is how your V out looks like. When you place your cursor over it, you can read the peak to peak value of it, that reads about 988.65 millivolts. So this is your voltage at the output. So this is how you see an inverted cosine waveform when you give a sine wave as an input signal to the differentiator circuit. So now let's close this circuit and go to the square waveform. Now I'm going to supply square wave as an input signal to the same circuit by keeping all the parameters the same. Okay, so this in this section you would have to choose the pulse option and set these parameters. After setting these parameters, click on save circuit and click on run. So here is your plot pin available for it, and I'll click on the V in Here you get a square waveform, and on the Vout section I'm getting the spikes available at the output terminal. So this is how when you give a square wave as an input signal to the differentiator circuit, you get spikes at your output. Okay, so we are done with the square waveform now. Moving on to the next, now I have the triangular waveform. So triangular input signal actually. So again, I've used the pulse parameter over here. I have just changed the insides of it, like the V initial to be -1, V on to be 1, delay to be 0, T rise to be zero point 0.5 milliseconds, T fall to be zero point 0.5 milliseconds, and T on to be 0, and T period to be zero point 0.5 milliseconds. So this is how you set the parameters, where the function available is pulse over here, and the AC amplitude to be equal to 1 volt. And you click on OK. Again, save the circuit, click on run. So this is again, you are loaded with a plot pane. Click on the VN, you get a triangular waveform, and on the Vout section, so you get some sort of a square waveform at your output. So this is how when you feed a uh, triangular input signal, you get a square waveform at the output terminal. So that's how we have seen the triangular waveform. Now let's go on to the frequency. So for frequency, I would be changing my simulation commands. That is, go on to the simulate tab, select edit simulation command. Then I have when choose the transient, since I want an AC analysis. I would go on to the AC analysis tab. I have taken the sweep to be of type octave, and number of points per octave is 100 in my case, and frequency is the starting frequency is 1 hertz and it goes up to 100 kilohertz. So this is the frequency parameters. I have click on OK, save the circuit again, and click on run. Now click on the Vout section. So you get you get the frequency plot, which is of a high pass filter. Now since the magnitude and phase plot are together, if you don't require the phase plot, you can right click over here and say that select the option of don't plot phase. So this will remove the phasor plot from the frequency response plot. So I mean to say the magnitude plot. So this is how your high pass filter look like. Very high pass filter response looks like, and this is how your frequency response is all about. So again, as I had done in the integrator prior, we can verify the values that at what frequencies I'm getting gain of. So like around, for example, if I'm at a frequency of 5.28 kilohertz, I'm getting gain of 12.56 in dBs, which is indicated at the bottom left corner of the tool LTSPICE. So where your X and Y axis are available. So you can read the values over there by placing your cursor over different points at your plot. So this is all about the frequency. So again, that's all as I've shown. And the phase response, if you don't want the magnitude plot, you can separately plot your phasor plot in the pane. Okay, so that's all my explanation regarding with this experiment. So we are done with it. Thank you.